All right, the primary displacement is this displacement where we removed the redundant reaction and it is being caused by the actual load. And now this is a case we could look up in a beam table and find an answer. Let's practice working with the moment area method though. And that means we have to go create the moment diagram, and that result of that effort would be that our diagram would be a second order curve that would be 0 and tangent out at the far right, and will be maximum at the far left, and its magnitude would be minus WL squared over 2, right? Total load is W times L. Its centroid is at the midpoint, so the moment arm with respect to the left end would be WL, or sorry, would be L over 2, so you'd end up with WL squared over 2 for that max moment. And for us, then, that would be 29.2 times our length of 35 meters squared, then divided by 2, or 17,885 kilonewton meters. All right, so that's our moment. Now, we really want the curvature for our moment area method. So M over EI, well, EI is constant, so the shape of this whole thing is the same, and all we're going to do then is divide by EI, and we have it already. Again, this is a second order curve that we are working with, right? And so our deflected shape that we have is consistent. And so when you go say, I want to calculate what delta BO is, then note that that is going to be the same thing as a tangential deviation. That's why I choose the cantilever to begin with. All right, so I draw a tangent to the elastic deflected shape back at A. I chose to do that. And so we're out here at B. And the tangential deviation at B with respect to a tangent that was drawn at A, YA, because I knew the slope at A was 0. And so that, and then I just make the observation that the displacement I want is exactly equal to that right there. So that makes things nice and easy. All right, so that's going to be the first moment of the area under the M over EI diagram, taken about the point in question. The point in question thing we're calculating is out of B. So let's get the area first. The area is, well, this is a second order parabola that has a vertex over here at the right with 0 slope, and it's the skinny part of it. So the area part, let's see, second order is one more than a triangle or straight line. So we go one more, instead of 1/2 base times height, we go 1/3 of the base, that's the length, times the height here, which is WL squared over 2EI. And it is downwards, so let's get that out there. And then we got the moment arm, and you might have to look that one up, but that will be 3/4 of L, right? And the triangle would be 1/3, 2/3. In this skinny parabola, it's the 1/4, 3/4. And yeah, if it was cubic, it would be 1/5, 4/5, as I recall. So we got 3/4 L there. Notice I kept it in terms of symbols because the numbers get really big, don't they? Right, so this is a 2. That 3 goes away. That with that 3, and we'll get a minus WL to the 4th over 4 times 2, 8EI for delta B 0 acting downwards. All right, now if you want to put your numbers in there, go ahead, but notice how gigantic for in the SI system these numbers are going to get. Minus 29.2 kilonewton per meter times our length, which is 35 meters raised to the 4th power over 8EI. And I know that the EI is eventually going to go away, so I'm not going to be messing around with it. And yeah, it's a gigantic number, minus 54,772,881. So let's see here, that'd be 5,477,281. And let's see, kilonewton per meter times meter to the fourth would be kilonewton meter cubed. So force length cubed, that's what that should be. It is. And then divide by EI. Whew. Wow, that's a lot of work. Not really, but seems like it.